Tuesday, Australian time that is, where we look at cool tech, we pull it apart, we do some reverse engineering, and we also design new open source projects. If you've been following along, you'll know that we've been working on a MIDI-fication mod for Strymon small box pedals. Now, of course, coinciding somewhat with the new sort of releases that add USB and sort of standard MIDI capabilities to these, it's still going to be a really useful and interesting project for all of the existing pedals out there that people maybe don't want to get rid of or don't want to spend another $400 just to get that functionality. And saving a lot of pedals from sitting in dusty drawers or possibly landfill. So here we are. Should be able to see my screen there. Let me know in chat if there's any issues. It looked a little bit pixelated on my end, but I'm not sure if that's just Restream doing its Restream things. So, cool. Now, where we got to last week. Last week we were looking at designing our own digital to analog converter, sort of. Now, let me jump across to our schematic. Let's dock that to the left and close it. Of course, I want to dock both of you. Anyway, so we're using Fusion 360 for this design process, namely because it's free for hobbyists, startups, they have educational licenses, so a lot of people are able to take advantage of that. It's not a perfect tool by any stretch of the imagination. It definitely has its quirks, which I'm quite vocal about when they come up. But overall, I think it's I'm just going to move that up a little bit. Overall, I think it's it's a pretty good tool for a lot of people, especially those who are getting started. If you're familiar with Eagle, then it basically Autodesk bought out Eagle. So yeah, feel free to follow along. And when this is wrapped up, I'll be putting the all the project files up on GitHub for you to peruse if you're interested to build your own, or simply just to follow along with the project. So where do we get to? We've got a couple of boards here. The schematic's still a bit of a mess. I tend to be really, really messy with my schematic layout as I'm going, and then I kind of tidy it up afterwards. Probably need to get a little bit better with that, but anyway. So we've got, we're building using a Raspberry Pi 2040, the RP2040 platform. It's the same same microcontroller that's used on the Raspberry Pi Pico. And we've got a, a basic bare bones schematic layout here. We've got our main chip. We've got some supporting decoupling capacitors for the main voltages as well as the core voltage. A reset switch. We've got our pull-up circuitry there. We've got our crystal oscillator network here. So, well, it's the crystal, not a crystal oscillator, with the loading capacitors and a dampening resistor there. We've got our quad SPI SPI flash there. We can drop a few different chips in here, but by default, we're just going to go with the 128 megabyte package that they sort of use in the hardware design documentation. Then we've got an SWD connector for programming, serial wire programming and debug. And we're using a tag connect, like spring-loaded type plug for that, so we don't have to add an extra hardware header on board. Next, we've got some user interface elements. We've got our potentiometers there, which are going into our ADC. Last week, we were also looking at the fact that the RP2040, unfortunately, only has 4 ADC channels. We need 5 channels for our 5 pots. So we're using a separate ADC chip for that, an MCP3008. We've got some LEDs for the foot switches, and we also added some underneath the potentiometers, just in case we might want to use clear shafted pots and do some color recognition on the controls, possibly. Can't hurt to have it in there. All right. Our foot switches, and then also the toggle switch with some basic debouncing there. I might increase those resistors to 5K or something like that, but here we go. Then we've got our our DAC channels, so DAC channels here. We've got the ADC chip. You can see we've got these ADC channels, and I'm making this a little bit general purpose, by design. Nice coffee on a cold winter morning, so that we can repurpose a bunch of this schematic for other projects. I'd really love to try and build a series of projects around the RP2040, maybe some MIDI controlled analog pedals. It'd be pretty cool, I think, to go through like a range of the classics, like your Tube Screamer, Rat, Big Muff, and MIDI-fy them and add a digital control board or something as some open source projects. That'd be really cool. So yeah, I've wanted to allow for extra ADC channels without having to do sort of too much redesign in the electrical sphere. So that's that. Then we've got this DAC section here, which is fed via a PWM output on the RP2040. So let's take a look here. Now I've got a sim. We were doing some simulation in LT Spice last week. Actually, I'm not going to go ahead and resim that. Watch last week's stream. We went through and spent a fair bit of time just trying out some different topologies, using like some bipolar junction transistors as digital buffers to translate that logic level, because there's some very specific set of requirements that are actually really uncommon in this kind of project. Because we're building only one half of a product, we're building a control board which has to interface with another PCB, and that we don't have any control over. I can measure like our reference version to check the voltages. So it actually is a 5-volt board, which was surprising, not 3.3 volts. And the supply rail was measuring at about 5.28 volts. So there's an extra 280 millivolts than what you would expect from a standard 5-volt rail, which is not abnormal. A lot of voltages will be a bit higher than that, especially depending on the loading, but presents a problem. One, we cannot fry, we can't afford to damage the, the main board by going over voltage with that. But because on the original, the potentiometers are just acting as a simple voltage divider from that reference supply, it's going to be expecting that full range to be swept, relative to a reference voltage on the main board, the chip that is reading those controls. And if we don't reach that full range, then it's going to sort of limit where we can go with that. You'll sort of ramp it up to full, but it might be missing the last maybe, 4 or 5% of that control range if we just put a 5-volt reference on there and assume it's 5 volts. So we need to kind of have this non-fixed reference voltage in mind. So what we've done is something a little bit interesting. Now we're using a MOSFET here as to convert our 3.3 volt, because that's our RP2040 runs on 3.3 volts. Using that to translate our 3.3 volt PWM to a 5 volt PWM. Now, say 5 volts. This kind of connection flag here is just quasi 5 volts, but it's whatever that reference voltage is. So for all intents and purposes, we'll call it 5 volts. But the beauty is that whatever that voltage is, this will shift it to that. Some pull-up resistor there. And this is exactly the same as your run-of-the-mill bidirectional, level shifter from SparkFun, Adafruit, so on and so forth. Doesn't need to be bidirectional, but it's 2 resistors and a FET. So, Then we run through this op-amp here, acting as a buffer with just a very small value capacitor there to act as, dampen some RF from getting into the feedback path of that op-amp, which is very sensitive. And the reason we need this op-amp is that we've got a 2-pole Salem key filter here, an active filter built around this other op-amp in the package. And the issue is, and we were showing this in the simulation, that you get some interaction between this filter and this level shifter, and this would be really easy if we were using our own dedicated reference voltage. We didn't have to use this 5 volts. We could use some closed loop gain on the op amp to shift our analog waveform up. We could do all sorts of things, but because we are limited by that, the best way to ensure that everything's going to be rock solid, our filter performance is really good, we can run a PWM at high frequency, all those sorts of things, is to use an op-amp buffer here to separate the level shifting from the filtering so that there's no interaction between the output impedance of this stage and the input impedance of this stage. So we've got here 5 PWM ADC channels, and I haven't duplicated those beyond what we need because it's a block that can be sort of copied and pasted, as opposed to choosing an ADC chip which has some extra channels, so we don't have to use a completely different chip. This can be a matter of copying and pasting. And I'm using, for this design here, an LMV324. And that is just pretty standard Jelly Bean op-amp, but it is rail to rail, which means it can swing its output all the way from the positive part of the supply to the bottom or the negative part of the supply. In this case, our 5 point whatever volts to ground. And that's really important because we need to make sure we've got full performance over that range. When I say performance, I'm not talking about crazy high slew rates and input like offsets and things like that. I'm just talking about being able to fairly accurately reproduce that waveform over the full swing. So this is this is our saline key filter. I'm not going to go into too much detail of this. We did a lot of that last stream, so if you're not sure, check that out. But that's our kind of our ADC and DAC section. Then here we've got our power sheet, which I haven't really fleshed out all that thoroughly. You can see it's still a little bit of a mess. But the idea is that, we've got our 5 volt input into the board. I'm going to go and add some extra filtering, probably just get rid of some of the high frequency noise. And this is going to be our nice clean 3.3 volts supply for all of our digital circuitry on board here. And that's where we are up to. So today we're going to be doing some PCB layout. You can see that the actual PCB is in a sort of a, not a sad state of affairs, but nothing's really laid out. It's basically just the pots are there, the controls are physically where they need to be, so we can get our, where's our 3D model? Hang on a second. I don't want to regenerate it because it takes ages. So we've got our controls that we can fit into our enclosure, but none of the actual components are, close to where they need to be. Let's open that. We've got, if you've been following along, we've got this daughter board for our USB and MIDI I/O, which is going to connect to the main board, so we can decouple the placement of that to the enclosure, so that you don't need to, they're not surface mount to the main board, which fits into the holes for the jack. So we can just provide a drilling template. You can kind of drill that more or less where you want. We'll provide either a FR4 template or a laser cut template. So you just put that on the side and drill, and with just a hand drill, you'll be able to do this project. No special tools required. Alrighty. So that's kind of the current state of the union. Let's go ahead. Going to add a label to this sheet here. Power. I like to just make some big labels on these sheets here. This is a part where I think Fusion could really get its act together here with like some native objects for sheets, rather than having to build these as part of a library. So you could have just editable title blocks and things like that. The Sage and Author and everything like that works pretty well, but Anyway, so we've got our 3.3 volt regulator, and this is just a standard SOT23-5 regulator. I'm going to take that out of the way here. I'd like to add a little bit more input filtering. So we're going to go ahead here to our place components. And what we might do is, so I'm using a library of components that I've sort of brought into Fusion 360. So we can do all these open source projects, and it should have everything I need along with ready to go 3D models. I'm going to bring a ferrite bead in here. We're just going to use that. So we're going to add the connector for our, let's go from here to there. Probably a little bit later, but I just want to get this laid out, and we'll play with these actual values a little bit later on. So we've got that ferrite bead in here. We're going to have our raw input sort of, reject some high frequency noise going to our 5 volt signal there. We'll come back to that because now we're going to start connecting things up to our Raspberry Pi. So let me grab a new window here so you can see my browser, because we're going to be looking at the RP2040 data sheet. If you want to follow along at home, RP2040 data sheet and RP2040 hardware design documents. Now, where's OBS gone? Because I'll get a, might have to bear with me here. Yeah, so that's not working full stop, but I'm going to bring my my face cam into here and also a window capture so you can follow along with what I'm doing. Bear with me for one moment. Got a new window open there. All right, OBS. Cool. Sorry, just bear with me for a second because I'm just going to duplicate this scene here so it's fairly it's not too dry. All right, now let's get rid of that window capture. I'm going to chuck this side one in here. There we go. All right, so hopefully that should kind of be displaying for you guys. All right, and if you have any comments, please comment. You know, I've got the chat window open, so if you have suggestions or ideas or you're not sure about something, the whole purpose of this is so that everyone can learn and everyone can follow along with the project. So if you'd like to know how something works or have a question, please drop it in chat. All right, now we want the RP2040 hardware design and RP2040 data sheet. And this is going to tell us everything that we need to know in order to start making some connections to our main chip and also get our PCB layout rolling. Alrighty. It is just a little bit. Let me resize that a little. Transform. Let's fit. Oh, no, we don't want to do that. So it's kind of going to cut the bottom off a little bit. Sorry about that, folks. Just because I am using it on a vertical window, but I'll try and make sure that everything I'm looking at is in this top section here. Okay, so first thing we need to do is I need to look at the SPI interface for our ADC chip. Now, we've obviously got our standard SPI connections. We've got our clock. We've got MOSI, which is master out, slave in, which is going to be going the data from our microcontroller to the ADC. Oh, let me clear that label up. That's a bit messy, isn't it? The data to our ADC. And then we've got MISO, which is master in, slave out, which is the data from the ADC back to the microcontroller. And then we, of course, have our chip select pin here. So what I might do, actually, I realized I haven't added a decoupling capacitor to that VREF, and that's the reference voltage from which it will process our analog voltages. So I'm going to add just while I think of it, 2 capacitors here. I'm going to copy a 100 nano capacitor and then also add a, sorry, let me switch back to the main screen. Sorry about that. Add a 10 nanofarad capacitor for, because we're really trying to filter out some high frequency noise here. We just want to add a slightly lower value capacitor so we can take advantage of where the those resonant peaks are going to be in this network and really filter out that noise effectively. And I might just go and drag this to the other side because the general rule of thumb when you're talking about decoupling and filtering capacitors is that you want to have the lowest value capacitors closest to the chip in order for them to be effective. So it's good to just sort of represent that in the schematic form as well as you can. All right. There we go. That's a bit better. Now we're looking at our ADC channels. So we need SPI. We need a SPI bus side screen. Let's take a look here. We want to find I/O. Oh, this is our hardware design. We don't want that. We want the data sheet detailing, you know, what pins are on what, because here it just says sort of GPIO, this and this. And I know it's got programmable I/O, but there's no point going to that level just to use pins willy-nilly when we can take advantage of the existing onboard peripherals. Programmable I/O peripherals. Here we go. All right, so USB. Yeah, that's going to be complex because USB is complex. If you've ever written USB drivers, not even low-level drivers, but just like class drivers, that in itself can be complex enough, let alone actually looking at the low-level information on the data sheet. UART, we don't want UART, do we? We want... that's I2C. Still I2C. Oh, come on. Where are you? Anyone? Should have just gone through the table of contents. Would have been quicker. Still I2C. Since when does that I2C need to be so big? SPI. Here we go. Okay, cool. I've kind of probably gone past the start of it here. Great. Oh no. Let's go back to the peripheral table of contents because I cannot find the start of the SPI section. Peripherals. SPI. There we go. Okay, so 2 identical SPI controllers. Now this is a dual core chip. There's 2 M0 Plus cores on board, so I'm not sure if you I've never used the RP2040 before, by the way, so you know, don't like, you know, if I'm missing something blatant, feel free to leave it in the chat. This is the first time I've worked with it. I haven't actually done a lot of work with you know, multi-core or like multi-threaded, not multi-threaded, multi-core designs where you actually have access to both the cores. You know, I've used like modem chips or Wi-Fi or Bluetooth modules where you have one core that's doing your, you know, the stack and the network handling, and then you have another for user application. But actually managing both cores is a little bit new to me, so that's kind of going to be interesting. Hey, and Restream doesn't show the... It's really annoying. Restream doesn't show the names of people kind of commenting, so sorry about that. Let me try and bring up a no. Bring up the actual thing so I can see the chat. All right, sorry, just bear with me a second because all I want to do is see the names of the people commenting. I didn't think that was such a egregious thing to want. So sorry about that. It's not gonna let me see it. Is it, unless you've commented on YouTube. Just a second, I want to get this sorted out because it's really frustrating not being able to actually see who it is that's talking to you. I didn't think that was, yeah, such a big thing. Okay, is it on YouTube? Let me bring up the YouTube chat. No, it's not there on YouTube. Is it on... in the event in our user group, maybe? I think that's probably it. Sorry about this. Okay, there we go. Oh, Andrew, sorry, mate. It was the very last source that I checked. So my apologies for that absolute dead air. Okay, great. Yeah, it's just super annoying the way that like Restream doesn't actually show. It's got to be to do with the API. But anyway, yeah, no, if you missed, I'm using Fusion 360 so that it's as accessible for everyone as possible. I, have had a fairly extensive background using Eagle, and I think that especially for open source projects, Fusion can, makes a lot of sense to people. I know there's going to be the KiCad kind of, you know, KiCad, Fusion, this and that debacle. KiCad certainly has come a long way. Not denying that at all. It's just I would rather spend the time on the stream actually designing something than learning how to use new design software. And that way, if people have questions, I can actually give them answers rather than say, I don't know, I barely know what I'm doing, you know, with this workflow. So yeah, but yeah, this is exactly the kind of thing that people see, you know, people don't really see behind the scenes working through. And it can be a little bit in the weeds, but I think it's actually really useful because unless you see this process, it kind of leaves you a bit shot in the dark, actually doing something like this for yourself. So yeah, let's go back and we'll take a look at our here at our spike. So I'm not sure if they're hard connected to each core or not. I would assume that we can define that in the marks. Yeah, we can say, so this is a description of how everything's connected. Don't really want to worry about that. So it has, you know, like FIFO for transmit receive, which is first in, first out, if you're not familiar. And that's really useful because it allows you to, you know, you don't have to have soft buffers chewing up RAM space and things like that. We've got a DMA interface. That's nice. I just have, this is the first time with the RP2040 and I have no idea what pins I need to connect it to, or if you just connect it to whatever you want and then you mux it in the configuration of it. That's nice. They've got some example code there in C of using the SPI interface. That's pretty cool. Like I think it's got some. Oh no, that's for the timer. Sorry. There we go. There's some example code showing that. Now this is all well and good. Oh no, that's PWM. What I want to do is just find the pin connections here. I thought that might have been relisted in the peripheral, but it's probably up here somewhere. Power state machine clocks, GPIOs, interrupts. Don't want a list of registers. I want a pin connection because I'm coming from an STM32 background where it'll give you a list of pins and a list of what you can, you know, like what you can connect. Oh, okay, thanks, Simon. It doesn't show people from watching inside the Facebook group. Okay, so that's like a Restream plugin thing. You know, there you go. Oh, there you go. So you've I'm using Altium for PCB design, and then, you know, SolidWorks for mechanical, electrical. Yeah, totally. And it's sort of pick your flavor a bit. I think that Fusion, if you're talking about mechanical design and 3D modeling, Fusion's definitely so much more accessible for people. And it's actually, that's where, you know, it's a really competent, that's its bread and butter, 3D modeling. Eagle had its quirks. A lot of those quirks have carried over into Fusion, and I think they were running before they could walk, in that they wanted to add all these new collaboration features, but they missed improving some key aspects like good library management, like just, you know, a few things where I think they'll get there, and it'll really be worthwhile. But yeah, there's a bit of that. I don't know why I haven't given that a value, because that needs to be 12 megahertz. So like, oh, I need to fix that right away. Okay, anyway, let's you can go there. Let's come back to that. We are looking, so that's, yeah, I'm coming from an STM32 background where you know, I'm not sure if it's done the same way on this, but there's a list of pins and a list of what you can connect to said pins, and then you sort of pick which ones you want to use within those, you know, within those restrictions. And maybe I'm just thinking about this the wrong way because I can't find okay, so that's RP2040 pin mapping. Hardware GPIO layout sheet. Well, that's for the Pico. I don't, you know, that's not really of much help. Pin mapping. Oh, I missed programmable I/O. But I don't want programmable I/O. I want the built-in peripherals. I wouldn't have thought that was such a difficult thing to ask. Yes, it's still PIO. Everything's pin mapping on PIO. Yeah, if you're doing, Andrew, if you're doing defense work, I definitely not what Fusion is is used for. I will guarantee you that. That's for sure. It's kind of interesting. I've always been a bit fascinated with, the type of just work and restrictions and constraints you have on you doing like, government contract work and things like that. Especially the thing that would just do my head in is the life cycle management and so my understanding is that you can't just, you can't swap in components. You have a list of approved components. At least I know for, like Dave Jones talks about a bit in his time doing defense work, for the Australian government. And you can only choose from these components. You can't even just something like a resistor. You can't sub in some other resistor. If you have a stock outage, it actually has to go through and be validated and approved and this and that. And man, the BOM management must just be next level for that. Anyway, all I want to do is know what pins I've got my SPI bus on. I didn't think that was that egregious thing to want to do. Am I in the SPI section here? I'm pretty sure I am. Push pull, blah, 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 blah. SEL, no, so SEL, so it's still in I2C land here. And it's really annoying. The headers on this document aren't good. It just says functional details. It doesn't actually tell you I know it says 3-point blah, blah, but then you have to memorize the pins that you're up to and things like that. So where on earth are we here? We're in a 3-point whatever. I'm pretty sure this is programmable I/O. I just want to know. Yeah, life cycle management is just one of my the acronyms I hear and just shudder at. If someone's familiar with the RP2040 and they would like to tell me exactly where I should be looking for this kind of information, please just tell me, because I'm obviously absolutely smooth braining this. Is it? It doesn't actually give you like an overview in the peripheral section. Okay. I'm going to Google SPI pins. Can't find it in the data sheet, so we're going to be looking at some other stuff. Configure SPI pins. Yep, Reddit engineering to the rescue, ladies and gentlemen. I don't want the Pico pin out. I don't want software SPI. I want hardware SPI. All right, I think we'll just go to the Pico pin out. And, kind of take a look from there. So SPI is our pink here. So SPI is 0. You can put on those GPIO pins. I'm just going to take this. We're using the Pico mapping. This is, so much time just trying to find this. So it uses TX and RX instead of MESO and MOSI. Okay, that's fine. So GPIO 0, I guess. I'm going to move this crystal and reset circuitry out of the way just a bit. Got some space here. Some flags to connect to these. What I do love about SPI is you don't need external pull-ups or things like that. And compared to something like the number of designs that engineers just get a board back and realize, oh, this doesn't work because they forgot external pull-ups on an I2C bus. Crazy. Okay, so we can so that's RX. That's going to be SPI MESO because it's the master device receiving the data. It says RX, so that's master in, slave out. yes, we want to connect. Oh, sorry, my text size is still enormous from my my sheet labeling. Yeah, SPI's great. The number of pins it uses for chip select, obviously not so much, but yeah. I'm glad you're enjoying, still enjoy doing the low level design, Andrew. It's, I love it. Don't need a master chip select, so we can ignore that. Then, okay, we can also GPIO 4 can be RX. We might just use that so they're nice and buddied up together. Although then it's going to use up a UART either way, I suppose. I'm just going to use these 3 pins here because they're next to each other, and that sparks joy when things are right next to each other. SPI, SEK. Using a new keyboard too, and by new I mean secondhand off marketplace for $30 because my nice Logitech G613 wireless mechanical keyboard has just had a ghost typing issue from the deepest pits for a while, and it's just been doing my head in. And this has the same layout, but it's not mechanical and it just feels garbage. But that's an aside. So GPIO, oh my gosh, okay. It's GPIO 2 that is our clock. My mistake. SPI. There we go. Now GPIO 3 is going to be SPI Mossy because that's TX and master out. And then SPI Miso for GPIO 4 because that's RX. Master in slave out. Then we're going to want a chip select line, and I'm trying to avoid, using up any pins that I don't need to. So, just have a look up here. I got an RTX 3080. Very nice. I mean, feel free to send me your 3070 this way because I'm using I've got an RX 480 at the moment that's firmware modded for 580 specs, and it's fine, but like running triple monitors is a little draining. Nobody, hello from YouTube. Yeah, the updated version with MIDI and 6th knob is hitting shelves very soon. Well aware of that. Covered that at the start of this stream, start of last stream, and the start of the stream before. Like I said, if for folks who are happy to go out and spend $400, $500 on the newest thing for that extra knob, by all means go for it. They're going to be great. They're going to sell like hotcakes, but that still leaves tens of thousands of still awesome kick-ass pedals with where people just want like MIDI control and things like that, and I think we're actually going to add some features here that would might even be a little bit better because it's open source. We can build from the community in terms of what it can do with this control interface, and that's really exciting, and it's going to cost like well under $100, so I think it's still got a lot of value. But yeah, if that 3070 shows up at my door, I won't be complaining, but enjoy your 3080. It's going to be awesome. Yeah, 3080 for $1250. That's almost unthinkable now, to be honest. Like, oh boy, it was like $1250 Australian for a 1070. A GTX 1070 from however many years ago. Anyway, we are getting sidetracked. So GPIO 5, I just want to avoid like stepping on any usable signals. Yeah, we'll make that the chip select line. We don't actually need that. So we'll make that ADC chip select there. Thanks, nobody. That's actually the name if you're watching. Thanks for the sub. Really appreciate that. If this is the kind of stuff you guys enjoy looking at, the engineering process and open source projects, like if you have an idea and you want to submit it for, not the GitHub repo isn't up yet, so I can't quite do a pull request, but, chuck your ideas in, things you think would be cool. By all means, like, please go for it. We want this to be not just an open source project that you can maybe build yourself. Because, if you're DIY, you can take the schematic and the Gerber files and get your own board fab to build it yourself if you want. It probably cost you like 20, 30 bucks, depending on where you source your components from. So, you know, but we want to have the full kit available, you know, assembled, ready to go for, as I said, under $100. That's the goal. And all you'd have to do is just like drill 3 holes using a drill template we, you know, provide. So very straightforward. Anyone should be able to do it. All right. So then we've got our SPI connected there. So we've got our ADC chip select. We've got our SPI pins. They're coming from our pots, which are, where are they? They are here. I probably should move, maybe I should move that ADC over to this sheet, maybe not. Anyway, ADC in 0, so on and so forth. Now let's look at our PWMs. Let's go back to our data sheet, PWM hardware. So I don't know if all pins are PWM capable on this. PWM block has 8 identical slices. Each slice can drive 2 PWM output signals or measure the frequency, reduce that input signal, sure. So 16 controllable PWM outputs. All 30 pins can be driven by the PWM block. That's handy. So we can put our PWM pins wherever we want. So what's a slice? Exactly. A slice. There's going to be so much of this, me just looking at the data sheet going, how exactly does this work? Yeah, so we know how pulse width modulation works. What we don't know is how a slice works. Clock divider, sure. Yes, that's all very nice. Does each slice... Okay, so when free running the period of PWM slice output. Gotcha. So I would assume each slice has its, that the period is kind of locked for each slice. Because all we need to do is change the duty cycle. So if we can apply phase adjustment, we don't need to worry about the phase of our PWM signal. All I want to do is make sure that we can control the duty cycle independently on these slices, because then we can just chuck them anywhere we, on any pins we want. Double buffering duty cycle. Okay. So I'm looking here. Oh, sorry, let me scroll down a bit. I'm looking at this bit here. 0 and 100% duty cycle, so it can be just toggle free. That's nice because then you don't have glitching. That's a nice feature. I just want to pulse width modulation. Cool. That's what PWM means. Toggled output. Alt behavior. I just want to look at what the slices are. PWM. And whether you can control the duty cycle separately. Because I'm gonna want to control the duty cycle independently. Two independent output channels. Okay, duty cycle, great. So each channel on the slices have independent duty cycle control. That's important, but they'll share the same counter period, which is fine because we're going to set the frequency common to those. I don't really know where I want to connect those because I haven't looked at physically how these are connected. I guess let's chuck. I want to sort of separate them from because something we're going to have to take into account here is keeping, good separation between our analog and our digital side. So, on one side of our PCB layout is going to be all the stuff going into the microcontroller, and then ideally we just have things that interface to the connector, with really good separation to avoid crossover between our digital and our analog signals. So let's just chuck these here for now, GPIO. We'll leave those ADCs there. We might want to use those for something. For now, let's just kind of whack some PWM channels here so we can get a feel. Because we can change this later, right? Once it's on the board, we can see, oh, actually, it'd be better if this connected here instead. So What are those referenced as? It's PWM 0. All right. Probably didn't need to add why is that big, but PWM 0. PWM 1. 3 and 4. Nice. I only just got around, or maybe I just have missed it, but adding nice options for labels here. Hang on, for like label flags like this, which is great, except that the default text size means that you can't, they don't work like that, which is just such an oversight in my opinion, because that's the standard spacing, pretty much pins on everything. 3070 is going my other machine that I'll put in the family room for room scale VR. That's awesome. I've been wanting to do a VR setup for ages, but it's just, even my like RX 4080 would run it. But finding a good VR headset that, has the features and specs and things like that you want, like, the Index, sure, that's pretty capable. Like the Quest 2, in my opinion, is such a good option for VR because it can do standalone, it can do linked to a PC. But, oh boy, the meta buyout makes that such an unappealing choice. Got to go for a run, finish a mix. See Andrew. Thanks for tuning in, mate. It was so good to just hang out and chat. With like-minded folks. That's exactly the purpose of this this stream. Enjoy, and we'll talk soon, mate. So we've got our PWM channels there, going to our DAC outputs. So PWM goes in, smooth analog waveform comes out. Perfect. What else do we need to connect up here? Let's have a look. We've got our switches. So foot switch 1, 2, toggle A, toggle B. Now, I'm going to be referring to this data sheet a lot. I'm assuming that all pins are interrupt capable. You would have to think that on, it's not AVR days where you get like the Atmega 328 where you get 2 interrupt capable pins or something ridiculous like that. That's silly. Very, very silly. Okay. Did I miss it? Peripheral. It'd be under GPIO, won't it? GPIO interrupts. Okay. For every GPIO pin in 4 scenarios, great. We get. Okay. Do we get the option of edge change? Because it says we've got level high, level low, edge high, and edge low. So we've got the transition there. I would assume that you can set it for edge high or edge low, so you get the interrupt regardless, but we'll get to that. Cool. Well, let's just whack them on, somewhere, and then we can change the pin out exactly a bit later on. You can go there. Now we'll add 4 pins for our 2 foot switches and our toggle switch, which needs 3 pins. Let I'll start from the top. One. Yes, we want to connect those. No, we don't want to use a label just yet because they're big and chunky. FS2. Did I call this toggle A? No, I obviously didn't. I called it toggle A no underscore. Got him. Toggle A. Toggle B. Now, something that you might want to just be aware of when you're designing systems with interrupts, and a bit of a gotcha, I don't know how it works on the 2040, but I know at least in the, so what was that? I've got the Index, the G2, and the Quest 2, though, with their pros and cons. HP Reverb G2, interesting. I haven't heard much about that, so good to know it's got some glowing reviews. Very, very nice. Anyway, what you want to be careful about with interrupts, this is a bit of a tip. I have been on the data sheet the whole time. I'm so sorry. I've forgotten to change back over to the main screen. My bad, guys. We just connected up some Spire pins, some PWM pins, and some interrupt pins. But take an STM32, for example. Every pin can be interrupt capable, but you'll often have multiple banks of GPIO pins. So you've got GPIO A, GPIO B, and they will be arranged in like a 16-bit bank. So you have GPIO A0 through to GPIO A15. And the way the nested vector interrupt controller, or the NVIC, works is it gets the external interrupt channel, and that's mapped to the pin number. So if you have, GPIO A3 and GPIO B3, they're both going to trigger the external interrupt channel 3 interrupt, and you have no way of differentiating which one is which inside of the interrupt. Well, as a return from the interrupt, you would then have to go and read both pins, determine which one, is high or low, and then correlate that to what the interrupt event is, which is fine. There are some race conditions, some edge cases where they might change at like the same time and you can't read them fast enough. Very unlikely, but something to be aware of. So generally you want to make sure that you're kind of interleaving your interrupts so that you don't have them stacked on the same interrupt line, just as a fun fact. I'm assuming with the Raspberry Pi it might work similarly, but that said, it's just GPIO full stop. So maybe not. It's 32-bit core. Maybe it just has a single 32-bit GPIO register. I don't know. Raw interrupts. Okay, so that just gives us 0 to 8. Okay, each IO status has a register followed by controller. There are 30 IOs, so the structure is instantiated 30 times. Okay, so there's 30 IOs, not 32. Oh, GPIO. It says it right here. Okay, so each one has a unique register by the looks of it. So you don't have to worry about running into that issue that I was just describing. Okay, cool. Well, good to know. What else do we need to connect up? We need our quad SPI, which is already connected up there. Our debug, serial wire debug is already connected up. We need our LED data there, and that's about it, I think. So for our addressable LEDs, we are going to want to use the programmable IO or PIO for sure, because I know that they've got detailed support for addressable LEDs. We're using some WS2812 2020 package ones here. So 2 millimeters by 2 millimeters. So they've got an example ready done for WS2812 LEDs. I often, the way I'm using it, so for like STM32 projects, which is what all of our, kind of non-open source Pirate MIDI products are built around up until this point, is I actually use a transmit only master SPI, and I set the SPI frequency such so that I can get the ones and zeros to kind of correlate to the pulses required for the WS2812 kind of protocol. And then I use a DMA buffer, which gives you really fast control of the LEDs. You can kind of just dump this big array of SPI data into the DMA buffer and send it and not have to worry about it. DMA is direct memory access controller, if you're not sure, and it allows you to offload tasks between different peripherals, such as reading an ADC into some memory, for example, without having to have CPU intervention for that. So super nice. It's a way of sending data from one place to another automatically in the background, so you don't chew up clock cycles doing it. But great, it's got a ready-made example for WS2812s. I love that. Love that. To DMA the pixel, it's got examples of that. Maybe we don't really need to worry about that too much. Anyway, that's great. That's really nice. Tell you what, the RP2040 would be useful for, because you get this TX RX examples here. No, I can't remember how many programmable IO blocks you have, but if you could just duplicate TX and RX and have some sort of like 8-channel UART chip, that could be really cool for adding heaps of MIDI channels to hubs or projects. Anyway, I think we can just use any pin, honestly. So I'm pretty sure we can. Let's just choose this one. I'm going to move our USB lines out of the way with our terminating resistors just to make space. I might actually, while I'm at it, add some labels onto those. There's enough space, and it just makes things look a bit cleaner, in my opinion, when you've actually got these nice labels going on. There we go. And we're using the N and the P after it to inform Fusion that they are differential pairs, and we can use some routing rules for differential pairs as required, even though they're very low speed. You know, it's just, I think it's USB 1.1 on the RP2040, so about as low speed as it gets. Let's make that, what does that need to be? LED data, I called it. Cool, so it's telling us the other sheet that it's connected to. Great. Yeah, it looks odd having these like labels and then just not labels, the way it's kind of worked out there. But anyway, save that just to double check, and that's looking pretty good. I'm liking the way this is forming up. I think that's everything connected up. What we can do is we can go to validate and run an ERC, electrical rule check. More than one output pin. I might have, hang on. This will be interesting. What have I done there? Goose. Oh no, it's just there's some, yeah, just Eagle not liking more than one output pin. Oh, it doesn't like that it's connected to sort of that pin and that pin of the op amp, I think that's the error it's floating. Let me switch back to the main screen here. So just running an ERC check, it doesn't like that. I know that electrically that's fine, so we're just gonna do that. Output and supply pins mix, that'd be, I haven't gone through in these Fusion libraries and, you know, set all the output, you know, all the pins to be the exact right type so it doesn't throw these errors. It's just a bit of a time sink, but I know all these just saying 3.3 volts is connected to something. Thanks. Only input pins on net. ADC 15, ADC 5. So that's just telling us that ADC 5, 6, and 7 don't have anything connected to them, which we know because we're not using them. So we'll go ahead and approve those. SPI, CLK. Oh, did I use SCK before? I think I did on my SPI. Why have I used CLK there? Whether using SCK or CLK sort of doesn't really matter. I like using SCK, so we're going to change that. It means clock, you know, serial clock, you know, whatever you want to call it. Cool. That's looking good. Now let me just go back to our ERC, rerun it. V minus connected to ground. Yep. Missing junction. Oh, so that's a good one. This is why you run an electrical rule check. I've kind of chucked these capacitors in, and it requires these decoupling capacitors for each of these pins. And, you know, it just a copy and paste or something like that. There's no junction here, which means they aren't actually connected. Really handy to note. So now that that junction's there, we can see that net is all ground. So that's that. I definitely wouldn't have caught that if I hadn't have done the ERC check. Honestly, I would have just missed that. And these aren't connected. We need junctions on those as well. So I think in copying and pasting things, it's just not connected things properly. So this is why you always do an ERC, electrical rule check, and DRC, design rule check. Friends don't let friends send boards away to be fabbed without doing both of those things. Only one pin. Yeah, I know there's only one pin on that. One pin. That's a good thing. We haven't added our USB yet, but we're going to get to that because we need a connector from a USB daughter board to the the main board, and likewise for MIDI. So I'm not going to approve that because I want that to stay there. PWM2, why is there only one pin connected to PWM2? There you go. Another good pickup by the ERC. I've copied and pasted, so PWM0, PWM1, and then when I've copied and pasted these blocks, I obviously, DAC out 1. I haven't changed these net names. So 3. Someone's probably, especially in watching it back when non-live, would have seen that and just been shouting at their computer. Go ahead and change that. Lovely. There we go. Now we know there's only one pin on reset. Okay. So I typically just sort of an auto fire, and for an SWD connector, reset is typically the name of the reset pin. Raspberry Pi, making things nice and user-friendly, has called it run. So we're going to need to change that pin name there to run. We'll call it reset. Run's the name of the pin on there. I'm going to make that reset there. We'll add put a little name there so we know what's what. Cool. Cool. Then these are just, powers connected to power stuff, which, yep, that's the idea. Power pin, yep. And so this, this model was from Snap EDA, so they, in fact, have sort of just YOLO'd with the pin names. Eagle throws up some, you have to be very meticulous if you want to avoid these kind of ERC errors, which honestly has an uninvoked gate. That's true. So we're using a quad op amp package. So we've got A, B, C, D, then of IC1, then A, B, C, D of IC2, then IC3. We've got these unused op amps. Maybe we'll use them for something. I'm going to leave that there, so I've got that error kind of letting me know that. And then R1 has no value. The pots. The pots don't have any values. We're going to use probably like 10K here, I'd say. Just overlapping, of course. Does the default position make that any better? Yeah, it does. All right, so to make this a bit easier to read, we're just going to select these caps out a bit. There we go. Now we'll go ahead and assign the value of 10K to all of these. And then we'll go ahead and use the restore position to put everything back in the, default readable place. For some reason, it's not. Maybe I copied and pasted over, something from another design. Say, relaying it out again in the schematic, and it just was like that. There we go. That's better. I'll go back to our ERC. Can you display the errors, please? It's gone behind for some reason. It doesn't show the ERC window in the window capture, so sorry about that. I'm sort of just reading them out to you. Unconnected pin on our ferrite bead. Yeah, I know that. That's fine. And our switch has no value. That's fine. I'm going to prove that. I'm going to go ahead and add a value to the ferrite bead. So I think that's good. That's good for now. So we'll go ahead and save that. Just give me 1 minute. Okay. That's looking good. Let's take a look at our PCB layout here, and we're gonna PCB layout here. We're gonna have a big mess of I'm going to go over to there. No, doesn't matter. A big mess of these air wires, which are like unconnected things. So, all right. First of all, we want to put some design rules in place. Now, We're going to probably use JLC PCB for this. This is an unsponsored stream or anything, so you can use whatever I like. That doesn't matter. Now let's go back to our browser window. JLC PCB. And take a look at what their design rules specify. So resources, support, capabilities, maybe. Where is it? PCB. Here we go. So this is where they've got their design rules. Now I've actually already got a file for their design rules downloaded here. And we can go into our PCB DRC. Let me just load that up and I'll show you. So it's somewhere. This is just going to be a two-layer board. All right. Go on here. Yes, it doesn't show this pop-up window in Fusion. I'll try and use maybe like a screen capture rather than a window capture for next week. So sorry about that. Anyway, we go check and we can see we had some design rule issues here on the spacing and tolerance or clearance of these, pads to the cutouts, but it's fine. It really isn't a problem. So this is our serial debug connector. So you can see it's got some outline layer there and they're indicating holes. And then when we actually drag it into our outline, there everything sort of kosher and updates nicely. So when we're doing, I just want to start doing some rough PCB layout here so that we can kind of just place things generally where they need to go and start seeing this take shape. And if we go back to the overall project, we were looking at where this daughter board could go. And I was saying that, well, this side here, there's a bit of kind of clearance in this cavity. If we hide the enclosure, we could mount it there to the enclosure and have, reasonable clearance on the PCB there. And then on the enclosure side of things, it's, where's the bottom part? Bottom, get around the top. It's got a reasonable kind of clearance from the top there, so drilling holes isn't going to damage the top of the enclosure by sort of blowing out there if it's too close to the edge. So that's pretty good. I think that space for the I/O is going to work pretty nicely. We can make that PCB Layout, that PCB there a bit more streamlined. Of course, we need to add our right angle brackets to it. But what we might do is we'll do that now so that then in our 3D model, we can look at where all our components are going to go. So if we switch back over here, this is the kind of the TRS board, and it's super bare, as you can see. I basically just chucked the connectors in and called it a day. So we're going to go ahead and find a frame here. Now I'm pretty sure I added some in screw fasteners. I added these right angle through hole select. Yes, that's what I want to place. Fusion, honestly. These screw fasteners, and we'll just put them there. And you can see the 3D model for those here. And that's what's going to allow us to fasten this board to the enclosure, nice and securely. That's not coming apart anytime soon. That's going to be extremely rigid. So to the PCB layout, we're going to need to make this a little bit bigger, that's for sure. So maybe it won't fit in that other spot. I hope it does, because it's kind of nice. I'm going to go ahead and add our design rules again, the exact same design rules from before, just like a JLC 2-layer design rule, so that I can move this. Now I've got it on a 1mm grids, because for mechanical dimensioning, I like to do everything in metric. And if you control and click, it will snap it to the nearest grid location. So let's just move all of this. Okay, let's just move. Whatever. Let's move the PCB down. I was trying to maintain it at the origin, but put that there. And we want it to protrude from the PCB just a little bit. And these connectors are probably going to have to push up somewhat, I'd say, probably that realistically at least there. And that's probably as small as we can, we make it a bit more compact, I suppose. Something like that. Probably is about as compact in that, kind of orientation as we can make it. So save that, and then we'll regenerate our 3D model. So push to 3D PCB. We're just going to use 3D PCB with canvases, so it's nice and quick. And I am just going to go and grab some more water. I will be back in just a second, because that's going to take a little bit to just generate. Sorry about that, guys. Just had to go and grab something. So, all right, 3D board is here. It's looking good. So these these right angle connectors are going to be awesome for fastening to the enclosure. Now looking back, like if they're all on the one side, that might cause some clearance with the PCB. So we'll see how we go. So we're going to save this. And I've already got this in if you'd like to do multi-board design or even just single board design in Fusion. So this is the overall project that we're working with, and it's got all these things in it. And this little exclamation mark means that the component's out of date. So now that I've saved that, it's going to, apart from this here, it's going to be like, there's a new version available. Let me know so we can go update to child components. And it's going to bring the latest version of these 3D models into the project. So you'll see that update there. So that's obviously going to cause some clearance issues. Now, by how much we can, and I've just roughly placed it, so I'm not expecting it to be perfect. We'll go to the inspect tool, click on point, and go there. Now we can see that in the in the Y axis, which is that one there, it's 1.518 millimeters. Okay, so it's also interfering with that part of the PCB. So, and then also the LED. Oh no, so the surface mount LED is there. That's fine. So what we're probably going to have to do is just be a little bit careful, maybe make a cutout of the PCB so that of this main board so that this can kind of go down into it. Then we're going to have to kind of carefully make some outlines so we can fit it here into everything else. I'd say is going to going to be what we'll have to do. So, you know, we can't really fit these two, you know, everything that much closer together. I mean, we could a little bit. Let's try and just see if we can consolidate things. I'm going to go to a 0.5mm grid here. We just bring these a little bit closer together. You know, they're not going to be at any risk of shorting. Like that's fine. Just bring those a little bit closer together. Then we can bring this in by a millimeter. In fact, I'll just give it a little bit of separation there. There we go. Just in case someone's like hand soldering this and make it as easy as possible for them. Can we take that outline all the way to there? Yeah, of course we can. It's USB connector. I don't really want to add too much more to it. Can take it in by 0.5 mil there. So I'm just, you know, seeing how much we can bring this outline down to reduce the overall footprint of things. Now I'm going to go and move everything. Actually, no, we'll do that later. Let's just look at the vertical position of this. In fact, you know what? I've used Eagle for like many, many years, and still I've never used or made good use of the measurement tool. Like measuring one point from another, and maybe it's time that I do start using that. Annotate. Anyway, whatever. I'm just going to get this position, the vertical, so it's 40.5 mil, and this is in the negative, so 2.5 mil. So it's going to be 43 mils apart, and these are M3 holes. So we can just go to our enclosure. On this side, I'm going to create a new sketch on this face. Okay, so we've got some M3 holes, 43 millimeters apart, and some height from the top. And we're going to do that just by kind of, you know, really guessing and checking. We're just going to put it approximately where we think it needs to be, and then see how it goes. So we've got our new sketch. Going to create a what's it called? A construction line here, so that I've got a you know, something to use as the midpoint for all of this. So there we go. Why is that kind of floating around? Oh, I didn't fix it to the midpoint. My bad. Let's fix that to the midpoint of that line. Ooh, it doesn't like that, does it? Again. There we go. Then so we want some circles. So we just place some circles here. Now we're going to add some constraints. We're going to make them equal. And we'll define this. If we're using M3, we'll make that, let's say 3.5, allow a bit of sort of wiggle room. They're both going to change now. We'll add some horizontal constraints so they're both in line. And then we're going to set these to be 33 mils. My good, or guesstimating or what? Okay, and now we've got this, we can set some sort of you know, distance from here to the center as to where exactly we want it. So, you know, it could be 10. And we can, you know, click and drag them here a bit. So from the top, actually, I'm just wondering where the best place to go from that. Yeah, I guess we'll just take it from the top of the enclosure, really. Let's make it probably going to be about 5 mil, I'd say, and that's realistically going to be more like probably more about there. I'm just trying to get a rough, you know, placement so it's not completely out. So I know that it's, yeah, let's call it 20. Might be close. Okay, and now we can extrude these two holes. Just take them at -2. I'm going to extrude these holes into the surface of our enclosure, and then we can fix our board to those holes. I'm going to save our enclosure. If you guys have any questions about this part, we're integrating some of the 3D models into our overall design. Like, feel free to you know, chime in, get the latest. We could do it inside of this, you know, this particular enclosure, but what I want to do is create more of a universal enclosure so we can, if we're doing this with which I'd like to for a blue sky or a dig or something like that, you just use the same enclosure. So we've got these holes here. Once Fusion's sorted itself out, because it is just loading bar frozen. So good. Really, really love that. Love your work, Fusion. Let's give it a minute then. Yeah, awesome. So good. Thanks, Fusion. Can you hurry up and respond? Side note, I finally watched Bohemian Rhapsody, the movie, the other day. Really enjoyed it. It's really good. But I've now just gone on a craze of loving the versions of a couple of songs from that, from the movie in particular, Keep Yourself Alive and Fat Bottom Girl. I thought those sort of, new live, like remastered-esque versions sounded really good. Really, really good. Is Fusion just done? Check our little task manager. Apparently Fusion's all good, it says. Okay. Doubt. Well, what's unsaved? This isn't ideal. Our control board's unsaved. Our schematic's unsaved. And Fusion's just absolutely frozen. Is there some sort of hidden dialog box? I can't even minimize it. Cool. Well, that's sort of a spanner in the works. I guess we're going to have to force quit that. Wait, browser process quit unexpected. Please check your internet connection. Yeah, of course I've got an internet connection. I'm streaming. We're going to wait for Fusion to reopen. This is great watching here. We'll go back to, I guess, the JLC thing here. We'll probably wrap this up in a minute. I just want to get a bit of an idea of how this is going to fit together sooner rather than later. Yeah, okay, so we've got recovery documents at least. That's something. That was weird. I've never had a crash like that where it just sort of is trying to run the compute on a 3D model, and normally it'll say I've crashed, close, which is frustrating enough. But I get some quite a few crashes if I'm running it on my MacBook. It's on an M1 MacBook, and so I don't know if it's a Rosetta issue or just a general instability in the way that it's written for Mac OS, but recovery document exists. Do you want to open the recovery file instead? Sure. We'll open the recovery file. Okay, anyway, I'm on. If you want to come and look at this process. Okay, let's close that. I don't care about those. All right, now we want to be a bit careful because we want to make sure that we don't save anything without the full file being open. Because if you save, you open a schematic separately without the PCB file being open, and you make changes, well, then you've got a difference between what your schematic says and what your PCB says. So you're going to get these inconsistencies. So you really want to make sure that you're not, not doing stuff like that. So that's our 3D model. All right, now this is our TRS board. We've got our schematic and our piece and our project. That's good. And then we've got project, schematic, PCB. We've got two control boards. That's interesting. They look identical. I guess we're going to close that one. All right. Everything's looking okay. Recovering from that crash. It does, Fusion does have some reasonable autosave functionality. I'll give it that. don't know why they changed these icons. They used to be a bit more color differentiated. Now you can't tell the difference between what's the PCB document and what's the project file. Like whoever decided that change should be made. Oh boy, terrible decision in this latest update. Now let's save that. Now we should pretty much be cool. So we're recovered pretty much. That's fine. We've got our enclosure. I'm just going to go ahead and open the enclosure file back up. 1 second.
Here you go. And so the strap was aligned.
Okay, sorry about that. Just had to say bye to my little boy. Cool. So let's open up the, where are we? We're on the Deco MIDI Enclosure. Oh, it's a bit chilly today. Cool, there's our enclosure. Now, let's take a look. Going back to our project here. Oh, geez, I lined that up pretty closely. I'm on fire today. It's obviously too high. It needs to go lower. But what we're going to do is create a joint, mechanical joint. Let's get rid of that control board so it's a bit easier to see. So I'm going to join this hole there to, I'll look at it from this side, to that hole in the enclosure. So they will be rigidly connected there, as you can see, like so. Click OK. Now, our measurements are a bit off. How did that happen? Is that the latest? Because I know I made some changes. Is that the latest version? Where's our PCB document? Yeah, everything's looking pretty squished up. What's that? That's 40.5, and then we have 2.5 mil. So that's because we've got the both directions. That should be 43. Did I not make it 43? Why is that not lining up? That's kind of interesting. Let me just double check that I in fact made it 43 mil. Okay, well, let's do some measuring here. So we measure from that hole to that hole. We get 43 mil. Lovely. Now, measure from, I want to measure the thread, that outer circle to there. Distance 44 mil. I think maybe it just didn't push properly. This is what I mean. That I want the PCB, not the project. Make them different colors. So I guess we'll just push that to the 3D PCB. I think that's what happened. I think in the crash, I didn't sort of push it properly. And so we don't have that latest version where I kind of condensed everything in a little bit. We'll see if this changes. Things shift position once it's kind of rendered that 3D model. Yeah, okay, cool. So our 3D model just hadn't been updated properly. So we'll save that and we'll bring in the latest version of that board. Everything squishes together. Lovely. Now on our enclosure, this should match up beautifully. Love that. Cool. It obviously has to go down quite a ways. Let's find out roughly how much. We want to add some tolerance, you know, for the enclosure, of course. Sorry, where are we? We're inspecting. Go from that point to there. So it needs to go down at least 1.5 mil that way. So it's not going to matter if it touches the enclosure because it's not going to be connected to anything. But we'll add. Let's add 2 mil just to be safe. Oh, we can probably get away with 3 mil. Now, what we're also going to do is add some holes for the other connectors. Again, we're just going to sort of, give it a reasonable approximation of things. I know that these require like a 6 or a 7 mil hole to go nicely. So 2.5 mils. So that is 11 mil, and then 19. So 11, and then 21.5. Let's add some more holes. And they are going to be 11. Should I just add the spacing between them? So spacing between them is what? 19 and 8.5 there. Cool. So 10.5 mil. And then what else have we got? We've got a USB connector, and this is going to have to be a round hole because it's designed to be drilled by hand, by someone. So it's not going to be a nice rectangular slot cut out, unfortunately. But that's what, 29.5. I'm just going to reference everything to that post because it probably makes more sense to reference it all to there because it's going to be flipped. So actually, this is the wrong way around. It needs to be. Okay. So 29.5 to 40.5. All right, cool. So that's 11 mils from there. I'll just reuse that. It's a bit of a caveman-esque approach, the way we're doing this here, but oh well. What was that? Measurement 10.5. Cool. So we just go. USB connector is going to be 11 mil from there. Keep that there, and then we'll delete that measurement. There's a method to this madness, I promise. We'll reference everything to that hole there. 32 mil. It looks a bit messy, and that's because it really is a bit messy. Now, they're going to be our... actually, sorry, no, because our 3.5 millimeter jacks are here. They need to be 10.5 mil apart. Undo that because... All right, so these two need to be equal because they're our TRS jacks. Those aligned that way and make them what 6 mil. We go in for a USB. It's probably going to need to be a bit bigger. Let's say 8 mil, roughly relative to where that hole is going to be. I don't know there. Ooh, why is that measurement? That's pretty funky. No, I want that to be fixed in that plane. Oh, wait, I say no, that's 11 mil. Okay, so it's confusing because it's mounted upside down. So, yeah, bear with me a little on this. Save that sketch, finish that sketch, and then make it visible and re-extrude these holes. And we're just going to, there's no point really, I think, spending too long just, measuring everything out right before you sketch it. You want to just get something rough that, approximately kind of, fits in, and then you can fine tune it later and see how everything's fitting together. I think it's much more intuitive and also a bit faster to work with to see how everything's coming together. So. Not bad. Pretty close. Now we can see exactly what our vertical dimensions need to be by measuring these two holes and looking at the offset. So distance is 4.75 millimeters. So where's our enclosure? Edit this sketch. Now it needs to be, we're just going to base it off these holes here, all right? So we're going to do everything off those holes. Which way? So it needs to go up. Ugh. 2.5, that's very random. I guess we'll kind of just make that, what did I say that was? How much did it need to go up by? 0.475. We're just going to round that to going up to 3 mils, I think. How about this? Holes are going to need to go a little bit bigger, I guess. Is there a radius on this connector that we can use? Not really. I want is vertical distance. Okay, well, we'll just kind of guesstimate it, I guess. Make it 5, maybe. See how that goes. Save that. Okay, we'll come into there. We had a couple of folks I was trying to post in another group and let them know the stream, but I think there's a bit of something going with the rules. Rules. Someone just wanted to come and check out the stream, so just trying to message them and let them know. MIDI page. Cool. Okay. All right. Now let's look at the enclosures again. Oh, so it's a bit too high. How did I get that? Sorry. Oh, the hole, the connector needs to go up. The hole needs to go down. Ugh. Okay, so that can probably come down a bit. Oops. So it really needs to go down to, let's say 2.1. And that will come down by like 2.5. This is sort of a bit of how I think it's just easiest to do some mechanical design where you're just guessing and checking on some measurements, because there's no, you could go through and get it exact to the nearest 0.1 of a millimeter. But the thing is, when you assemble a board using, a surface mounted board, the actual connector is not going to be perfectly exactly centered where you think it is, because there's a bit of tolerance in the mounting holes and this and that. There's wiggle room that you need to account for. So there's no point in, getting it right to the nth degree. So I'm just going to take 0.2 of a mil off there. And, probably another quarter, another quarter of a mil off there. And I think that's probably going to be doing pretty good. So 1.9 is close enough, and we'll make that 3. See how that goes. And like I've finished the last couple of weeks, I was saying that this is tricky because I want to make it so that anyone can do this just using, like a hand drill, and we'll include a drill template to make it as easy as possible. Still needs to come down a bit there. Nice. They're nice and centered. Still needs to come down a bit, probably another 0.5 mil. And so unfortunately we can't, expect people to do a nice rectangular slot. Like, it's not easy. Not everyone has like an aluminium router. So it's going to be like a drill template that you put on the side, and you just drill these holes, away you go, and then maybe some sort of faceplate to cover it, and keep it looking nice, or maybe on the inside, so it's just a nice black surface. I don't know, something like that, because the rectangular cutout for the USB-C connector isn't the best, but I didn't want to use the only USB connector that works nicely with circular cutouts is the old USB Type B, like the printer plug type things. And they're just abhorrent for pedal boards. They're so big and chunky. So I'm going to need to make that hole a bit bigger, probably an extra mil, I'd say. Out for the connector in there. It's a little closer to the top of that enclosure than I would like, but it should be okay. You know, with a drill template, like I don't think that's going to be a big problem. And, you know, I'll do like a video sort of guide showing how to, you know, do the assembly and things like that. So it needs to fit through the hole. So again, it's just slightly too much, so probably another 0.5 mil in order to do it. So 9.5 mil. Again, that's closer to that top of the enclosure than I really would like. We might try and bring it all down a bit if we're going to do a cutout on that board anyway. Where's our control board gone? If we're going to sort of cut out around, it needs to go that way anyway for the pod. So we can probably make that whole thing lower by a fair bit anyway. So let's make that like 10 mil. 2 mil, if that's better. I like that a lot more. And then we'll probably make that 10 mil just for, you know, so the connector's not going to have any issues if it's, you know, just slightly misaligned or something. You know, you've got the tolerances of the through-hole brackets, then you've got the tolerance of the SMD connectors, and then the, you know, drilling tolerance allowance and all sorts of stuff. So having a bit of extra room is certainly not going to hurt things at all. Let me close that sidebar in a second because it's just extra real estate. Do not freeze again. I swear I'm going to be so cranky. Oh, come on. Are you serious, Fusion? This is why people get mad at Autodesk, honestly, because they just stuff like this. And a lot of this, I'm fairly sure, is because of you know, it doesn't like being disconnected from the cloud, even just for a little bit, and then you just run into all these issues. And it's like, yeah, cool, I get that you want cloud connectivity and collaborative features and all that, but maybe just focus on making a stable app first would be a great start. You know, like what's going on here? What's this? It's crashed again. Great. Well, anyway, we are getting to, you know, it's coming up on 2 hours of streaming now. This is not making for good viewing with, you know, Fusion. Just I should have saved those before I pushed it. Although it's only the enclosure saved, actually. It's only this that's not saved. We'll try and recover it and see if we can just at least kind of bring a satisfying close to this. So it didn't like something in the network connectivity, which is, you know, it just drives you insane because, like, seriously. But hey, who are we to judge? While that's popping up. No, there's no need to recover that because it's all we've changed is components that are being brought in, so we can just update that. No, don't want to update. Bring in a recovery document. I'm just gonna, yeah, we'll just update the everything. So at least we didn't really lose any work, so to speak. Oh, our enclosure didn't save. That's sad. Why didn't our enclosure save? Oh, we'll make another change to it. Put it there, 10. I'll just make that like 9, and then we'll go back to 10, and then it's going to say, oh, look, that changes. Ta-da. Update model. Oh, no, it did update the enclosure by the looks of it. Yeah, okay, my bad. It just that join hasn't, missing the reference, which, so it's got a reference for, hang on. That most recent one. Oh, it didn't save that join. Okay, that's why it hasn't updated that. Cool, so we're going to join this, which is going to be the reference for sort of everything, that connector to there. So that's what was lost in the crash. I also like having a bit more tolerance there. I could probably do with a little bit more, in fact. I don't think that's going to be a bad thing. That's going to be enough clearance around the USB connector. That's pretty good. Then there's some wiggle room in the drill and the screw holes there. Okay, cool. So we've got a little bit of, that's going to be about 0.5 mil, I think, between the PCB and the edge of the enclosure. Close enough. That's going to be good. Now, the USB-C connector needs to protrude through the enclosure a little bit. It depends on the actual connector that you're using, but because if it's too far in, then you're not actually going to be able to connect a cable into it properly. So it needs to come a little bit sort of protruded through the enclosure just a little bit more. Otherwise, the plastic housing of the connector won't be able to be inserted properly. There's a specification for the USB Type-C that details that, but it's pretty dry viewing to bring that up. So instead, I'm just going to shift this forwards like 0.5 mil. And that's going to be just fine. While we're here, how's everything else going? In terms of where the connectors are. Okay, so the 3.5 mil connectors could come in a little bit by the looks of it. How much? Let's find out. 0.36 mils. Actually, everything's like odd measurements, by the way, because of these like these right angle brackets. They're not, I think they're like 5.08, so they're using an imperial from where the pin is to the front face of it. So I believe that's why we're getting some real oddball measurements here. So instead of bringing the USB connector forwards, what I might do is actually just bring those. The USB connector only needs like another 0.25 mil of clearance. So I might actually just bring those back a touch. From there, rather than bring everything forward. And then we can 0.5 mil to make it easier. Bring 0.5 mil there. And everything, I probably could have just taken the connectors forward, honestly. A bit more clearance on the PCB. And if we save that and push it to our 3D model, I think that's gonna play nicely. And why I like to nitpick over the mechanical design of things quite a lot, because I want to know exactly how it's going to fit together before I put, a single trace down. Because if I do all of this work on a nice PCB layout and then I have to, make another cutout in the PCB for something to fit, well, that's so much work and time wasted. Whereas if I can just capture the, the essentials of what needs to go where and work around that, it's going to make life so much easier down the line. So, it seems like, well, we've spent half an hour, 45 minutes just nitpicking placement of stuff. Why? I'm going to save this, by the way, for my lesson, Fusion. It's actually worthwhile. I think it's, kind of time spent in reconnaissance, seldom wasted. I think time spent in 3D verification or 3D validation. Time spent in 3D validation is seldom wasted. That's my new mantra. Because I think it's really true. It's a really good use of your time to make sure you don't double back on yourself. So that's looking pretty nice. It's going to be 0.15 or something of 0.1. That's pretty much flush. Good enough. 2. That USB-C connector can probably come forward another 0.25 mil just in terms of the tolerance for that, but it's actually within spec now in terms of the cable insertion. So that's fine. Play around with that a bit later. But now that matches or marries to the enclosure nicely, we're going to need to shift everything a little bit, this way. Clearance for that pot, so that's fine. How much exactly? So I'll measure that edge to there. And again, these are 3D models, so they're approximate. You don't want to take them as gospel. There's some sort of rotational skew on that. Oh, the PCB's slanted by, I bet, you know, I've not selected one of the corners. Yep, there you go, when I'm clicking and dragging. So that needs to go there. There we go. It doesn't really matter. I'm not going to bother generating a new model for that. Let's just bring that 2 mil this way. So how far are we from? Lost my. Just make some, clean this up a little bit. Okay, let's make that 23. See how that goes. Save that to. See which ones? Which one? My PCB. We're going to generate our new 3D model just to clean that up, and then we can bring them all into our project file. I think is probably going to be the best way to do it. What do you guys? You know, feel free to leave a comment if you're new to the stream. Say hi, even if it's just a, you know, hey, so and so. Love to, you know, want this to be a really collaborative, communal experience in designing this, not just you know, watching me do my workflow. Do you guys have any projects going on at the moment that are interesting, or you know, if you're here, you are somewhat DIY minded, or at least just interested, you're DIY curious. Take that what you will. You know, what are you guys working on? Any fun projects going on out there? While we wait for this to compute. Okay, that's a bit of clearance from the pins. I'm happy with that amount of clearance because these pots do fit fairly snug. They could definitely do with some more, I'd say, but I'm not going to lose sleep over it because that switch sits below the surface there. That's going to be pretty nice. So we need a board cut out. Ooh, we are pushing the tolerance to that switch, but I don't think it's going to be a deal breaker. But what we might do is just look at from, where's that edge, from that edge of our bottom board. Can you give me the, let's call it 10 mil. What we're going to do is create a rough cutout to just, you know, sort of a quick and dirty, let's make some room for this. So document line, we're going to go 0 line width on the dimension layer to just create a kind of a vector cut. Ignoring those components there, it's going to have to be pretty close to those pins, unfortunately. Space them out a bit. Oh, is that going to be an issue? Let's go back. Hang on. Is that pot clearance going to be an issue? Ah, no. Well and truly fine. So probably make it there. Dan, I've just finished my first MIDI project. It's just on an Arduino Nano. Cool, awesome. That's so exciting. Yeah, Arduino is a great place to start on your first MIDI project. Is just like a, you know, a kind of simple controller or a looper, or you know, what's going on with that? Simon, building a couple of different clones. Yes, you do like those. Special germanium diodes from Russia on Etsy. Okay. Are they legit? I mean, how much the you know, magic source sniffing special diodes play in the role of a clone is sort of up for debate, but you know, it's definitely cool to get some old parts like that. That's for sure. All right, so we'll delete those extra lines, and now we've got a cutout that I think should work. Okay, so we'll save that. Push a new 3D. So I want to make sure this is going to fit together properly. Well, that's computing. I'm just going to check chat. So make sure I haven't missed anything. Lovely. So now we're going to have that cut out. So if that's where the USB is going, I would suggest that our 2040 probably going to go somewhere here, like right in there, because the connector to go to the main board is going to be about there. Let me grab the... So this is the old PCB, if you're not aware. See if that's going to... A little bit blown out. Sorry, I'm trying not to blast everyone's eyeballs. So yeah, it's going to be there-ish. So looking at it visually, there's definitely enough room for the 2040 to go in there. Then it's nice and close to the USB connector, and nice and close to that main connector to the rest of the board. There isn't really any need for an actual 2040 because we're going to be using some hardware for the signals, which reminds me, something we had forgotten to do is add some... I think I would like to use a separate chip to handle the foot switch emulation from the control board. Whether we just use some FETs, some discrete logic, or like, a buffer IC. I don't want to couple the RP2040 directly to it, even with some, logic level protection. I don't think that's a good idea. Dan, a loop switcher. Awesome. Cool. Yeah, I've had a project, this is like 6 or 7 years ago, where I used a Teensy and built like an audio looper with some MIDI control as well. Yeah, great first project. Feel free to reach out if you need any pointers with it. That's for sure. I was thinking that another gizmo, another open source project could be fun to do, is like something like that, maybe a 3 or 4 loop switcher controller type thing. Anyhow, enough yarn. Let's save that. Bring that in. See how that looks. I don't know. Maybe it's just that I'm a very visual person, very visual, hands-on learner. Need to see how things are laid out in front of me. It's weird that pad's cut off. Where's the 3D model with that? I thought I fixed that. I feel like Han Solo. Apparently not. There we go. I've just kind of potatoed that. We'll update our 3D model. I'm going to update both at once just so I can make sure that everything's going to mechanically fit together. So we'll probably go, now I'm sort of rolling with this mechanical and physical layout. We'll probably roll for another 30 minutes, I think, on this design. I do have a whole bunch of stuff, mostly hardware assembly of bridge 4s and the MIDI through gizmos to get assembled and shipped out. So can't spend all day on this, but it's fun. It's exciting. All right. I'm waiting for a compilation going on in the background, for something to compile for some firmware and app testing. So, okay, cool. We did not need the cutout to be that big. We can definitely add some board back to that. But, let me get rid of the enclosure. SMD connector, nice compact one there, and then a ribbon cable over to them. Oh, actually, that's right in front of the pot. I think what we're going to have to do is swap the USB-C connector there, because we're going to need a connector from the board to there, and it's going to be, make the best use of space if we put the connector right in front there. And we want to keep our USB data lines as short as possible. And it's not really possible to put it there because we've got this pot here. Yeah, that's not great. Okay, so, but that it's fitting together nicely. So what we might do is go back to our TRS board. I'm going to round some of those or take a little bit off the board in general, really, to just be a bit more streamlined. There'll still be enough room for a push. Actually, might not be. Might just extend the board a little bit in front of the USB-C connector, but I just want to reduce that mechanical interference. That's going to fit nicely, and then we'll just add a again zero width. On the dimension layer, we'll just add a bit of a right angle. There we go. And a bit of a, what's that? All right, 2 mil. So yeah, maybe just a 5 mil bump. A notch. Ha! We're embracing the notch design philosophy. How do you all like that? Delete that. That's looking pretty good. Oh, I had to swap it for the USB connector. Ugh. Duh. So what's that? 29.5. So I'm just going to, do these ones. Can go a bit closer, and that can butt up against there a bit, and then a USB goes into there. Except I didn't check the vertical alignment for it. Where is it? That's 11 mil. Okay. Oh, and then we'll drag this down to say here. Nice room to put like an FPC ribbon type connector down there, along with some of the couple of components for the USB circuitry. It's looking a bit better. All right, I'll double check the. So where's that? That's 9 mil now. So if it's been, let me just get my bearings for how this is fitting together. So it's now that away, and it's 9 mils from that one, which means on our enclosure, if we edit this sketch, we'll do all this at the same time. That needs to be 9 mils from there. And that is 30. What's that? 2.5. Okay, so 27.5. There's a more sophisticated way of doing this measurement. It's just, kind of 27.5. Bit easy. It's just the way that I've kind of do it. Oh, oops, that's the other one. 19.5. So that's okay. So that's 16. So we'll definitely overdid that. Oh no, I've got to add those together. Having an absolute shocker today. 19.5. Okay, so 22 is our enclosure. 22, and they're still 10.5 mils apart. I don't think I changed their relative spacing. 30, yes, they're still 10.5 mils apart. So that should fit together with our new enclosure. Emphasis on the word should. No guarantees. How are we tracking? So by the end of, in 27 minutes time, we should have all of our, both PCBs fitting together nicely in the third dimension, and the enclosure cutouts fairly well worked out. And that gets us onto the actual, layout of the electrical components and whatnot for next week. Cool. And our enclosure can be. We'll finish that sketch. Save that. Now, when we load and bring this in here, we can focus on niceties like making the board a cool shape and optimizing the design and all sorts of stuff later. But for now, we just want to get the thing fitting together. Doesn't matter how nicely designed it is. And it's done this again. This loading bar crash. All right. Well, I think we might actually end the stream there. It's doing my head in why this particular project is, doing. It's like, Fusion's chunky. It's using 6 gigs of RAM, just Fusion. Running 32 gigs in this system, and Chrome being the pig hog it is another 3.6 gigs. And because we're streaming, at like 35% CPU utilization, but it's not a computer bottleneck. It's just Fusion being Fusion, but everything else is saved. It's just this, fitting together. So we haven't really lost any work, but that'll be the stream for today, guys. Thank you so much for watching. I hope this was useful, interesting. I know had a few hiccups along the way. I think we're yet to have a stream where Fusion doesn't wig out on something. And not exactly a ringing endorsement, but like when I say it's you can get a lot done in Fusion 360 for both hardware and electronics design. This might have been a computer issue. Usually I find it's pretty good. It has its hiccups every now and again, but it is what it is. But yeah, thanks for joining. Next week, now we've kind of got the mechanical design fitting together nicely. We're going to be laying down all these chips and connecting them all up and really starting to bring this project, to life. So stay tuned. It's going to be same time next week, Tuesday, 8:30 a.m. Australian Eastern Standard Time. And see you later. Bye.